Alright guys, kia ora. Today we are doing the Level 3 Chemistry paper from 2020 on thermochemical principles. So opening that up, having a look. First question, okay, we've got a question about boiling points and how they relate to the forces between substances. Identify all types of attractive forces between the particles and of the following substances in their liquid states. They're all liquids. What are the forces between them, and obviously how do they relate to these boiling points? Okay, so here we've got a molecule, and here we've got a molecule, and here we've got an ionic substance. The calcium being the metal was the giveaway there. Okay, so this molecule is going to have, like all molecules, it's going to have temporary forces. Okay, and this is going to have temporary forces. So how come this has a higher boiling point than this one? Well, obviously it's a larger molecule, so that's going to be the answer there. This is polar as well. It's tetrahedral shape with asymmetrical arrangement, so that's going to have permanent because it's polar. This is non-polar, so it just has temporary. And here, really large boiling point. This is ionic forces between those. Okay, so now we can answer this question with reference to the relative strength of the attractive forces between the particles. In each substance, justify the following. Why does calcium bromide have a higher boiling point than these two? Ionic forces is the answer here. So this is just due to ionic forces are much stronger than the weak intermolecular forces. Okay, and so then just to say one more thing, because we're talking about boiling point, once we want to relate the forces back to that, so we're going to say the forces are stronger, therefore more energy / heat to break. Just making that link between the temperature going up and the forces that we're breaking. Okay, why does bromine have a higher boiling point than bromoethane? So the interesting thing here is that two forces here, one force here, but this one's got the higher boiling point. So despite the fact that they both have temporary, only CH3Br has permanent, but, and it's a big difference, but the molecular mass of Br2 is much higher. Okay, molecular mass leads to what? Leads to an increase in number of electrons. Increase in number of electrons leads to an increase in the size of the electron cloud. Increase in the size of the electron cloud leads to an increase in the size of the force. Okay, so that's why that one has a higher boiling point than that one. Alright, next question. Solid sodium hydroxide readily dissolves in water. This is the equation here for sodium hydroxide as a solid turning into aqueous ions. Calculate the temperature change. Right, so we're looking for a temperature change. When this much solid sodium hydroxide, we're given it in grams, we'll probably have to convert that to moles at some stage, dissolves in 35 grams of water. Assume the specific heat capacity is that, assume the mass of sodium hydroxide is that. Okay, so once we add that to that, we get that. Alright, first thing, let's convert from grams to moles. So number of moles equals mass over molecular mass. So this time that many grams there, we're just going to use that figure to calculate the number of moles. 1.7 divided by 40, put that in the calculator. 0.0425 moles. Okay, so 1 mole gives off that much energy. How many how much energy we're going to get with that. So let's just do that calculation. 1 mole was that, how much energy from that? So we're going to go, that is Q equals 0.0425 times 44.5. Alright, so that is 1891.25 joules of energy. Okay, note I've converted from kilojoules there to joules here. Because we're going to go into our next equation, we're going to use the formula that we get on our data sheet here. Q equals mc delta T. Q equals mc delta T. This is where we plug in these numbers. You note that we're working in grams for mass and working in joules per gram for the C. And so we want to be working in joules here with the Q as well. Okay, that's why I've converted to joules there. So rearranging this, because delta T is what we're looking for. Delta T equals Q over MC. Okay, delta T is the change in temperature, Q is the amount of heat given off, and M is the mass of the whole solution, the whole system. Okay, so we'll plug the numbers in. 1891.25 divided by the mass of 36.7 times specific heat capacity of water, 4.18. Alright, 12.3283 degrees Celsius. That seems about reasonable. I'm going to believe that is the correct answer. I'm going to round it to 3 significant figures at the end. And so look, this is going to be an exothermic reaction. It's going to give off heat. So increasing by it's only a small amount of water, isn't it? So increasing by 12 degrees Celsius seems believable. Alright, turning over. Next question, heating curve showing the change in temperature of a sample of stibnene. So we've got this heating curve. As we're adding more heat, the temperature is going up. Constant amount of heat over a period of 6 minutes. Cool. Write the equation for the reaction that has an enthalpy change equal to the standard enthalpy of vaporization. Okay, standard enthalpy of vaporization question here. So we're just going to put SbH3. Vaporization is liquid turning into gas. Okay, SbH3, I'm sure some of you know what vaporization is. Liquid turning into gas, alright. And we're going to do this question now. Reference for the heating curve of the physical changes between points A and D. Okay, so point A there, up to point D there. We need to talk about how the particles are moving, and we need to talk about forces. Alright, so let's just have a look at this graph and break it down here. So we've got these 2 plateaus, right? And we've got these 3 slopes. So obviously the coldest temperature, this here is going to be the solid, this is going to be the liquid, and this is going to be the gas phase. All right? So as we go from A to B, what's happening? A to B, the liquid is increasing in temperature. Okay, so in terms of particles, that's what's happening. We've got liquid particles. What's happening? They're moving faster. And there are intermolecular forces being broken. Right, so as these intermolecular forces have been broken, the liquid's starting to move faster and it's got more and more energy. Okay, from B to C, what's happening now? B to C. So this is where the temperature is not changing even though we're adding more energy. Okay, so why would that be? Because we're at the state change. This is where the state change boundary is happening. Okay, and so the energy is being used to break the intermolecular forces. Actually, I'm going to take that part out of this because while it's true, because some particles are actually turning into gas, it's probably not relevant really, because we really want to emphasize that that's happening at this state here. So energy is being used to break the intermolecular forces between molecules. Okay, and that's why the liquid's turning into the gas. And then D, it's now a gas. Okay, so that's what's happening here. This is a liquid increasing in temperature. Particles are moving faster and faster. Here we're adding more heat, but we're not getting an increase in temperature because that energy is being used to convert from a liquid to a gas and break the intermolecular forces. We need that energy to break those bonds. And then here we've got a gas forming as well, and the gas is increasing in temperature, and the particles are moving faster and faster as well. I'd put that down there too. Okay, moving on. Got a enthalpy calculation here. Calculate the standard enthalpy of formation of stibnene given this equation. Alright, so for this question here, what we want to use is this equation. So the delta RH, the enthalpy of the reaction, is equal to the sum of the enthalpies of formation for the products minus the sum of the enthalpies of formation for the reactants. Now we've just got to plug our values in. This is the enthalpy of the reaction. That is negative 1868 equals, the products are on this side, the sum of them, so SB203, the enthalpy of formation of that is negative 720, plus the water at negative 286, but notice we've got 3 moles of water, so it's going to be plus 3 times negative 286, okay, and that's going to be subtracted by 2 SbH3, whatever the enthalpy of formation is for that, which is what we're trying to calculate, right? Why do we not include water? Because it's in its elemental, oxygen. We don't include oxygen because it's already in its elemental form, so the enthalpy of formation for it is 0. You know, you can't go from pure oxygen to pure oxygen with, you're not going to get any change in energy with that. Alright, so at this stage we're just going to rearrange this and do a little bit of maths. So I'm going to put my SbH3 on the left hand side. That's going to equal a bit of maths here. Three times negative 286 plus negative 720. I'm going to add that to this side to get rid of it. Oh no, I'm going to have to add that over there. I'm going to keep that as a negative. I'm going to keep that as negative. That goes there. That goes subtract 1868. So negative 2 SbH3 is negative 290. So SbH3 is equal to half that. So the reason I'm doing the divide by 2 here is because two of those, and that's going to equal 145. Changing the signs because I want to get that to not be negative, and so I'll change that sign there as well. So that's now positive as well. 145, let's go back and put my units in as well. What are we measuring these in? This is your kilojoules per mole. Alright, so does that seem like it's sort of in the ballpark of these numbers? Yeah, roughly. Good. Moving on. How would the change in enthalpy for this reaction differ if water was produced as a gas rather than a liquid? Okay, so this water here is coming out as a liquid. If it was a gas, how would this change? Well, let's think about this. First of all, this is exothermic, isn't it? Okay, so it's giving off energy. This reaction is releasing energy. If a liquid was changed to a gas, that would require energy to break those bonds. So if we're using up energy by converting this liquid to a gas, this is going to give off less energy. There's going to be less energy available. So the answer is less exothermic, or less negative, because energy is used converting the liquid water to the gas. Alright, so that process would use up energy, and that would be less exothermic. Okay. Calcium added to a test tube of hydrochloric acid solution. Alright, it's an acid and a metal. HCl, calcium reacts vigorously, test tube becomes hot, bubbles of hydrogen gas going off. This is a classic experiment, you've done this in class before. The reaction is represented by the equation below. Okay, this isn't going to be important, this hot part. Justify in terms of entropy change of the system and surroundings why the reaction is spontaneous. Alright, so with questions like this, when we're talking about the system and the surroundings and spontaneity, we need to understand the concept of entropy. Entropy is sort of the randomness of a system or the surroundings, okay? And if a reaction is spontaneous, then the entropy of the universe, which is system plus surroundings, must go up. Okay, so with this reaction, this heat here tells us that the surroundings have increased in entropy. So hot means increase in entropy of surroundings. As in, the surroundings have got, like the gas on the outside of the test tube, the air in the room has gotten slightly hotter. It's moving faster now, it's got more energy, therefore there's more disorder, more entropy in the surroundings. The system is this reaction here, okay, so let's look at this reaction here. What we notice is that we've got hydrogen as a gas on the right hand side. So the system has also increased in entropy, and the reason for that is we formed a gas. Okay, gas particles are more random than solid. Then finally, okay, if the entropy of the system and the entropy of the surroundings have both increased, then the entropy of the universe must have increased. Therefore, this is a spontaneous reaction. Okay, electron configuration. So often when I do these ones, I like to start just by writing down my little mnemonic device that helps me remember. 3s2, 3p6, 3d10, 4s2, 4p6, 5s2. Okay, and we'll get up here a table out as well for this one, so we've got that ready for us. And remember the order that they fill was the 1s first, then the 2s, 3p, then 3s, sorry, that should be a 2, shouldn't it? 2p, then 3s. 3p, then 4s. Now remember, that's a really interesting one. The 4s fills before the 3d. Okay, then 3d, 4p, 5. Okay. Manganese, let's find that here. So we're just going to go with AR in square brackets, as that's our noble gas. Then dropping down here, this is my 4s2 shell, and this is my 3d10 shell. So I'm going to put down the 3d5, 1, 2, 3, 4, 5, and then 4s2. Arsenic. Okay, in the same row, along much further. So again, I'm going to start with AR, because that's the noble gas in the column above. AS is here, so we're going to go through 3d10, 4s2, and then 1, 2, 3, and my 4p shell, 4p3. Cu2+, okay, this is a tricky one. We remember that chromium and copper are tricky. So if we do the copper one to start with, the regular copper atom, it's AR, then 3d9, we would think, 4s2. Okay, but remember that it's more stable to have a completely full shell, as in that's a 10, and that's a 1, and 1 half shell, then it was 2 one full and 1 completely unfull. So chromium, copper are those unique ones. So the copper atom is 3d10. But that's not the answer yet. We need to get to the 2+ sign. So we're going to go AR. Now it's going to lose from this 4s shell first, and then from the 3d shell. So we're going to go 3d. Let's get rid of that, and we need to get rid of one of those. 3d9. All right. So that's the answer for copper. Remember that copper and chromium are tricky. Okay. Why do the magnesium atom and magnesium ion have different radius? And look how big they are, quite a big difference here. Well, this is easy. Let's look at the magnesium atom here. First of all, what can affect the radius? Protons can. But these guys have the same number of protons because they're both magnesium atoms. Same number of protons, therefore same nuclear charge. But Mg2+ has lost 2 electrons, and in doing so, it's lost the whole valence shell. So the valence electrons are closer. And therefore smaller. Okay. Lewis structure. BRF3, we've got 4 in bromine. Sorry, we've got 4 times 7. That's how we're going to do that. Bromine and fluorine both have 7 in their valence shell. We've got 4 times 7. That's going to be 28. We'll chuck a bromine in the middle. 1, 2, 3 for fluorine. F. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, that is 8 times 3 is 24. I've accounted for. I need 4 more. So I'm going to chuck them in the middle. Okay, and name of the shape. So it's based on the trigonal bipyramid, but it's only got 3 bonding. So this is going to be a T shape. P in the middle, 1, 2, 3, 4, 5, 6. I'll do the maths first. 5 plus 6 times 7 for the chlorines, plus 1 for the charge, and that's going to give me a total of 48, I think. Cl, 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 Cl. That is 48, 8 times 6. So we're done. Square brackets and a charge on the outside to show that it's PCl minus. The shape here is octahedral. Alright, on to the last page. Compare and contrast these shapes. Alright, so I'm going to do a little table. This is probably not how you want to answer it, but obviously I'm just doing it quite fast here. Regions of electron density. How many regions of electron density? This has got 4, this has got 5. Okay, what happens with these regions of electron density? They repel each other maximally. Okay, and so therefore the angle is here 109.5, and here we're going to have 90 and 120. So therefore the shape is tetrahedral. This is tetrahedral, and this is trigonal bipyramid. How many bonding regions? Oh, this one here's got 3 bonding regions, and this one here has 5 bonding regions. How many non-bonding regions? Well, this one here's got 1, this one's got 0. Therefore, the shape is what have we got here? Tetrahedral, missing 1, trigonal pyramid. And then 5 bonding regions. This is a this is the trigonal pyramid, and this is a trigonal bipyramid. So this looks like 2 of these stuck on top of each other a little bit. Right, so polarity. How are we going to work this out? So first of all, we're going to talk about the fact that the AS to F bond is polar. Why is it polar? Different electronegativities. In ASF3, there's a lone pair. Therefore, bonds are asymmetrical. Therefore, dipoles don't cancel. Therefore, the molecule is polar. With ASF5, we're going to say kind of the opposite. There are 5 bonds. All of the bonds are polar. Because of the different electronegativities between AS and F. However, the bonds are arranged symmetrically around the central atom, therefore they cancel out, therefore the molecule is non-polar. Alright, last one, ionization energy question. This is 1 mole in a gaseous state, losing 1 mole of electrons, so it's forming AS gaseous, positively charged plus an electron, so that should be an arrow. Alright, difference in ionization energies. With this question, let's look at what we've been given first. Nitrogen, arsenic, potassium. Now they'll always do this where it forms like an L shape or a T sort of shape, so that the astenine and the nitrogen are in the same column, and the astenine and the potassium are in the same row. So we'll use that as our talking point, the arsenic. So arsenic compared to nitrogen. What we see here is that they're in the same column. So arsenic has more protons, which gives it a greater nuclear charge, okay, which generally would increase the forces required to ionize, to remove an electron. However, it's also got extra shielding. Okay, so you can see that it's down a few rows. So extra shielding, valence electrons are further away. Therefore, decrease ionization energy. Right. Now we're going to use arsenic and compare it to potassium again. I wouldn't compare nitrogen and potassium. It's not an easy comparison to make, but we'll go from arsenic to potassium. Okay, so AS to K. Now, in the same row, so in the same row we're going to say same energy level. So therefore, same shielding, but arsenic has a much greater nuclear charge. That's due to the protons. Therefore, greater pull on valence electrons. Alright, and that's us. Hope that was helpful, guys.